of today. So today we'll be talking about the relationship between f of x, which is the cubic function, and f prime of x. So as you can see, I have drawn the graph of f and f prime of x. So for example, let us say we are given that f of x, let me give you specific values. F of x is equivalent to maybe x cubed minus 4x squared plus 5x minus 3. So if you can notice, this is a cubic function because you can see the first term is a cubic. It's cubed. So if we are given a cubic function and they say we must derive this function, when we derive the function, it's going to give us f prime of x, which is equivalent to 3x squared minus 8x plus 5. That's how we derive a function. I hope all of us will all know how to derive a function. And then let us notice something. If you can check, the moment you derive a cubic function, it gives you a parabola. Where the moment we derive a cubic function, what do we get? We get a parabolic function because we can see we have ax squared minus bx plus c. So we can see we have x squared and then x and we have a constant number. It means this is a parabola graph. So now we want to understand what is the relationship between f of x and what and f prime of x. So if we're with the moment we need the turning point of a cubic function, we derive the function, and after deriving the function, they say at the turning point. We're gonna say at the turning point or for stationary points. For turning points, for turning point, or for stationary point, we know at the turning point f prime of x must be equivalent to 0. Why is it equivalent to 0? Because at the turning point, the gradient is equivalent to 0. Then you're just gonna equate f prime of x to 0. You're gonna say 0 is equivalent to 3x squared minus 8x plus 5. Therefore, you solve for x. Then that's how you get the x value of the turning point. But now let us take f prime and treat it as a regular or a random graph of f. Let us say g, we are given another graph which is g of x is equal to, which is equivalent to, maybe we are given g of x is equal to 3x squared minus 8x plus 5. Note that I just took that graph of f of prime, then I treat it as a random graph. The moment we are given the graph of g, all of us, we can see that that graph of g is the same parabola which we found it using the cubic function, which is the first derivative. If we need the x value on g, what we're gonna do for the x-intercept, what we're gonna do is that we're gonna say for x-intercept, we let y is equal to 0. And it means g of x is gonna be equivalent to 0 because we need the x-intercept. And it's the same way that we get the turning point using the cubic function. Because using the cubic function, in order to get the turning point, you will have to derive the function and then equate the function to 0. Then it means the parabola, which is the graph, which is the first derivative, it shares x values with the turning points of the cubic, because to get the x turning points of the cubic, you must derive the function and you get the parabola. After getting the parabola, you say at the turning point or for stationary point, f prime of x must be equivalent to 0. Therefore, wherever you see f prime of x, you're gonna put 0 and solve for x, which is the same way we get the x intercept of a parabola when we're given that graph as a random graph like g. Then we're gonna just say for x-intercept, y is equivalent to 0. Wherever we see y, we're gonna just substitute 0, which is g of x. Then it means now the cubic function, our cubic function, when we derive it, we get the parabola. But what is the relationship between the two? The relationship is that when we derive a cubic after getting the parabola. The x-intercept of the parabola is equivalent to the x turning point of the cubic. They don't share the y value, but they only share the x turning point and also the x-intercept, only the x values. That's what we know. Now we want to understand something. We want to understand why does the cubic increases when we're given the f prime of x. Remember, f prime of x is also a gradient of a tangent on the graph at any point in terms of x. So if we can check, the cubic function decreases between the turning point. This side, it is decreasing. It is decreasing between the turning point. Then outside the turning point, it is increasing. Outside the turning point, it is increasing. Even this side, it is increasing also. So what do we notice about the cubic when it is increasing outside the turning point and it decreasing inside the turning point? If you can check, I drew that graph with red color and blue color. What does the red color means? It means where you see the red color, that's where the graph is decreasing. And wherever you see the blue color, that's where the graph is what? Increasing. But now let us talk about it, comparing it with the f prime of x, which is the derivative of the cubic. So now, if we can notice very well, the cubic function increases where the graph of f prime, which is the parabola graph, is greater than 0. The moment the graph is greater than 0, the graph becomes greater than 0 when it is above. Where the graph of f prime is positive, that's where the cubic is increasing, because the cubic, I mean the parabola graph, represents the gradient of the cubic. So it's gonna increase where the cubic is what? Positive. So where the cubic is positive, the graph of f, which is the cubic, is increasing. Where the graph of the parabola is negative, that's where the cubic is what? Decreasing. We can see where the graph of f prime of x is below the x-axis, the cubic is what? Is decreasing between the turning points, which is the between the x-intercept of the parabola. Because between the x-intercept of the parabola, the graph is below the x-axis, is negative. Hence, it means the gradient of the cubic function is negative between those 2 points. So the graph of f decreases where the graph of f prime is below the x-axis, and it increases where the graph of f prime is above the x-axis, where it is positive. So that's the relationship we need to know. If they say they wanted the values of x for which the graph of f is increasing, and you are given the parabola graph, which is the f prime. So you have to know that the f prime, the relationship between the f prime is that where the graph of f, which is the cubic, is increasing, it increases only if the graph of f prime is above the x-axis, and decreases only if the graph of f prime is below the what? The x-axis. As you can see on the graph, where there is a red line, that's where it is below. Then the cubic, between those 2 points, is decreasing. Then where there is a blue line, that's where it is above. It is positive, the graph of f prime. Then the cubic at these 2 points is what? Is increasing. That's what we notice. So the cubic will only increase if the graph of f prime, which is the gradient of the cubic, is above the x-axis. When it is below, that's where the graph is what? Decreasing. And remember again, the cubic and the parabola graph, they share the x-intercept. The x-intercept of the parabola graph are the x turning point of the cubic function. That's what you need to know. So the graph is either decreases inside the turning point or outside the turning point, between the turning point or not between the turning point. That's how we know the parabola or that's how we know if we're given the first derivative of a function drawn for us. Then they say they want the values of x for which where the graph is increasing or decreasing. They can give you maybe the x-intercept of the parabola. They say this side we have -2, for example. Then the other side we have maybe 5. Then they say for which values of x is f of x. We are talking about f of x, but what are we given? We are given the x-intercept of the what? The x-intercept of the parabola. They say for which values of x is f increasing. So what we know is that f will only increase where the graph is positive. When I move from the point where x is equal to -2, going to the left, we can see the graph is above, and this is where it is positive. It means x must be less than -2, or when I move to the other x to the other x-intercept, and I move from that x-intercept where x is equal to 5 to the right, that's where the graph is also again positive. So it means x must be greater than what? 5 again. So the graph will increase where x is is less than -2 or x is greater than 5. But between the x-intercept, that's where the graph is what? Decreasing. This is for increasing. Then between, if they want for decreasing, I will say for decreasing, the graph of f will only decrease where the graph of f prime is below the x-axis. If you can check between the x-intercept, that's where the graph is below the x-axis, where it is negative. So it means for decreasing, we're gonna say x must lie between what? Must lie between -2 and 5 in order for the graph to decrease. Note that, guys, if your solution lies in between, you cannot write that solution as two solutions. You only have one solution if you have your solution lie between 2 points. You only write two solutions when it doesn't lie between those 2 points. So if it lies in between, it means you're just gonna have only one solution. Take note of that. And I think this is what I wanted to talk about today. And thank you for watching the video.